Good morning to all of you. Today I am going to cover the video lecture 24. This content is developing with the help of JNTK Kakinada and Andhra Pradesh State Council of Higher Education. So today I am going to discuss the numerical problems on second law of thermodynamics. So in the third unit, the basic concepts what we have discussed once again, recapitulating the main points. So the first one we have discussed what are the limitations of a first law of thermodynamics. Then how you can overcome the limitations from the first law and it will be applied to the second law of thermodynamics. And in the second law of thermodynamics, some of the basic definitions, some of the basic concepts which you need to learn is thermal reservoir, heat engine, heat pump, parameters of performance, second law of thermodynamics, that is connected to this one, the Kelvin-Planck statement, Clausius statement, and its equivalence, corollaries of the second law of thermodynamics, perpetual motion machine of a second kind, Carnot cycle, Carnot's theorem, and the thermodynamic scale of temperature, and the Clausius inequality. So the Clausius inequality is going to discuss whether the cycle is reversible or irreversible or impossible cycle. So connected to this one, we will solve some of the numerical problems. So there is a first problem. It is mentioned that cyclic heat engine operates between a source temperature is given, sink temperature is given. What is the least rate of heat rejection but per kilowatt net output? That means W net is given per kilowatt net output of the heat engine. So this is the given problem, and for all these types of a problem, first thing is you need to draw the heat engine diagrammatic sketch. So once again recapitulating the heat engine, that is this is the source, and the heat engine is operating between the source and the sink, and it is taking some amount of a heat, rejecting some amount of a heat, producing network output. So this is what the heat engine. Heat engine is nothing but it is a cyclic device operating between the source and the sink, by exchanging heat from the source and rejecting some amount of heat to the sink, it produces some network output. So this W network output is nothing but equal to Q1 minus Q2. So if it is a Carnot heat engine, if it is a Carnot cycle, Carnot heat engine, then we may write that is the efficiency is nothing but equal to W net divided by heat supplied. So that is nothing but equal to Q1 minus, in terms of the temperatures, that you need to mention for the Carnot, it is so that is here, and this is T1 minus T2 by T1. T1 minus T2 by T1. Then the efficiency of both are same, but you just go observe this one. So here the W net divided by Q1, that is equal to Q1 minus Q2, Q1 minus Q2 by Q1. So this is in terms of this one, heat supplied minus heat rejected divided by heat supplied, right? So in another way, that is where you can mention, that is T1 minus T2 divided by T1, that is equal to Q1 minus Q2 divided by Q1. So that try to observe the temperature. So now what you have to do? So you have to perform the efficiency of a reversible, because it is the cyclic heat engine, and the efficiency of a efficiency, that is from this case where you can get the maximum efficiency, because the Carnot cycle is going to give the maximum efficiency. Carnot cycle is going to give the maximum efficiency, that is T1 minus T2 divided by T1, and all the temperature values. See here, this is the temperature source, it is 800 plus 273. This is the sink is 30 plus 273. So this is what you have to, all the values you need to make it as calculations in Kelvin. So here it is 1 minus the T2 by T1, that is equal to 1 minus T2, it is 30 plus 273. So 30 plus 273 divided by 800 plus 273. So you will get the maximum efficiency. You will get the maximum efficiency. So that is here W net divided by Q1. Maximum efficiency is 0.718. 0.718, right? So this 0.718 is nothing but equal to W net divided by Q1. W net divided by Q1, right? So what is the least rate of heat rejection per kilowatt net output? Per kilowatt net output. So if you just observe that, W net is given as W net is given as 1 kilowatt. W net is given as 1 kilowatt. So from this case, where you can get the Q1, that Q1 value is where you can get, it is 1.392, 1.392, right? So what is what we know, that here W net is nothing but equal to Q1 minus Q2. So that is 1 kilowatt is given, 1 is equal to Q1 is 1.392 minus Q2. So with this one, the Q2 value, that is the least rate of heat rejection, answer Q2 is equal to 0.392 kilowatts. See, always the units is very important. 0.392 kilowatts. So this is the least rate of heat rejection. So that is, this is the least rate of heat rejection, right? So this is what you need to find, and this is nothing but equal to 0.392 kilowatts. Whereas in this case, it is a W net, that is already it is mentioned in the problem, that is per kilowatt net output. So this is nothing but equal to 1 kilowatt, right? When you solve this particular one, where Q1, that is the heat supplied, you are going to get it as 1.392. So 1 out of 1.392, 1 kilowatt is the output, net output, and 0.392 is the least rate of heat rejection. 0.392 is the least rate of heat rejection. So this is how you have to solve the numerical problem. So already it is the heat engine. Next one is the heat pump, refrigerator. So all these problems already we have discussed in the earlier video lecture, right? So here the problem, sometimes the problems may be of combination type. That is, heat engine is connected to the heat pump, or refrigerator and heat pumps are connected. Refrigeration and heat pumps are connected. So here it is, one problem is given that a domestic food freezer, that is a domestic food freezer, maintains a temperature of minus 15 degrees centigrade. The ambient air is 30 degrees centigrade. Heat leaks into the freezer at the continuous rate of 1.75 kilojoule per second. What is the least power necessary to pump the heat? So this is what you have to find. So food freezer. So the problem is given on domestic food freezer, maintains a temperature of minus. So here also you need to draw that means it is the refrigerator type. So that is which is going to be operating between the source and the sink, and this is the refrigerator. This is the refrigerator, and it is going to be operating. See here the directions. These directions are very important. So just only the Carnot heat engine directions are reversed. So that is where we can call it as a reversed Carnot heat engine. We can call it as a reversed Carnot heat engine. That is, here you have to give some work input. And what is the given here? This is the freezer. So this part is nothing but freezer or evaporator part in a household refrigerator. So this freezer, it is given it as the T2 is equal to minus 15 plus 273. Minus 15 degrees centigrade plus 273. So it is 258 Kelvin. 258 Kelvin. And this is the temperature. So here the ambient air. So this is the ambient air. The ambient air temperature is, so ambient air temperature, that is the T1 is, it is around 30 plus 273. So it is 303 Kelvin, right? So here in household refrigerator, this is the portion where heat is rejecting. So the condenser tubes. So if you just observe the condenser tubes, where that tubes are giving the heat rejection to the atmosphere, right? So this is what it is given. So the food freezer, that is the ambient temperature is given, and the freezer compartments is given. So now what you have to do, observe that if heat leaks to the freezer at the rate of, so the basic fundamentals here, heat leaks. So this is the amount of heat leakage, that is Q2. This amount of that is from the outside air. That outside air is going to enter into the freezer at the rate of 1.75 kilojoule per second. Kilojoule per second. Kilojoule per second. So the refrigerator is going to the refrigeration cycle is going to removes the heat from the freezer compartment to the outside air, to the outside environment. So for that one, some work input is spent, right? So from work input is spent. So that means whatever the heat is leaked into the freezer, that leaked heat has to be thrown out. That leaked heat has to be thrown out. So it is not possible. So for that case, you need to do some work to the refrigerator, so that this refrigerator is going to remove the heat from lower compartment or from lower temperature to the high temperature. So here, what is the least power necessary to pump this out continuously? So for minimum power, the condition. So here, this is the formula everyone has to remember. For minimum power requirement, for minimum power requirement, what it is? The formula is Q2 by T2 is equal to Q1 by T1. Q1 by T1. So with this case, where you can get the Q1 value, right? So Q1 is equal to Q2 T1 divided by T2. Q2 value is 1.75, T1 is 303 divided by 258. 258. So you will get it as a 2.06 kilojoule per second. 2.06 kilojoule per second. Right? So the W net is nothing but equal to, it is Q1 minus Q2. See here. This work spent is nothing but equal to Q1 minus Q2. So what is Q1? 2.06 minus 1.75. So what is the answer? It is 0.31. 0.31 kilowatts. Kilojoule per second, you can call it as a 0.31 kilojoule per second, you can call it as a kilowatts. Right? So this is the answer. This is the answer. So the problems must be, here. The what you have to observe from this case. For minimum power requirement, this is the formula. That is, this is what it is to be striked in your mind, right? This is what every student has to remember this point. So this is the one type of it, and observe the day-to-day life. That is how these systems and systems, mechanical systems are interacting with the environment. So what is the heat absorption, what is the heat rejection, or what is the amount of atmospheric heat, or what is the amount of heat leaks into the refrigerator in when you open the household refrigerator, then the outside air is going to be entered. And but if you want to maintain the refrigerator at -4 degrees centigrade, if the outside atmosphere is 30 degrees centigrade, and that it is 30 degrees centigrade heat is continuously leaks into the refrigerator, then how that refrigerator is going to maintain at -4 degrees centigrade? So to maintain it as the -4 degrees centigrade continuously, then what the refrigerator has to do? So with the help of a compressor, where some work input is given, so that with the help of that work input, the heat can be transferred from low temperature reservoir to the high temperature reservoir. Right? So that is the one problem. Next one is the combination of the two problems. So here, combination of the, so it's a big problem, but the combination it is going to give the very good insights onto the second law of thermodynamics. So that is, you can get both the coefficient of a performance and the coefficient of performance of a refrigerator, coefficient of performance of a heat pump, and another one is efficiency of a heat engine. Efficiency of a heat engine. So try to observe this efficiency of a heat engine and what is given. A reversible heat engine operates between two reservoirs at a temperatures of 600 degrees centigrade and 40 degrees centigrade. Right? So let me draw this particular thing. Reversible heat engine. So first let me draw that particular reversible heat engine. So if you draw the diagrammatic sketch, then it is going to become very easy. So that is a heat engine is going to be operated between the source and the sink, right? So this is the source and this is the sink. So the source is 600, right? So 600 plus 273 is equal to, it is 873 Kelvin, right? And this is the heat engine. This is the heat engine, and the sink temperature is 40 plus 273. That it is, this is 313 Kelvin. 313 Kelvin. 313 Kelvin. Right? So now this part is over. This part is over. Come to the second part. What is the second one? The engine drives a reversible refrigerator. So this engine is going to drive a reversible refrigerator. Engine is going to drive a reversible refrigerator at which operates between the reservoirs at a temperature of 40 degrees centigrade and minus 20 degrees centigrade and minus 20 degrees centigrade. See here 40 degrees centigrade and minus 20 degree centigrade. Now come to here, the refrigerator, and the refrigerator is going to operate between this one and now here 40. So because here it is already it is mentioned as a 40. So I will connect the same thing to this one. I will connect the same thing to this one so that the directions are connected, right? So here you forgot the directions. So this is the Q1, this is Q2, this is Q1 and this is Q2. But the refrigerator here, one thing that you have to observe, it is, this is operating at minus 20 degrees centigrade. So minus 20 plus 273. It is equal to 253 Kelvin. So this 253, that means here the heat is extracting. Heat is extracting from this case. That is here I will consider this one as a Q4, and here it is rejecting to this one, that is Q3. So this Q3 is nothing but equal to, and whatever the work output is there, so that Q3 is equal to W plus Q4. W plus Q4, right? So but this now you try to come here, try to observe the another parameter. The heat transfer to the heat engine is 2000 kilojoules. So this is 2000 kilojoules. So it is a combination problem. Combination of heat engine with the refrigerator. Sometimes combination of heat engine with the heat pump. Sometimes combination of the refrigerator and heat pump. So that combinations are there, right? So the heat transfer to the heat engine is 2000. And the net work output of the combined engine refrigerator plant is 360, right? So out of which the combined, so this is the combined, that combined is it is going to give